Hello. This video will explain what an analog joystick is and how to use it with the Raspberry Pi. You can use a joystick in a variety of projects ranging from gaming devices to motor control. An analog joystick allows the user to provide information to a computer about direction and intensity. This is in contrast to digital joysticks and D-pads, which are essentially collections of momentary buttons which only provide direction. Raspberry Pi is a purely digital device, and it cannot use analog devices such as this joystick directly. You need to employ an analog to digital converter chip to interface it with the Pi. I will be using the ADS7830 chip in this tutorial, but you can adapt these ideas to another analog to digital converter very easily. If you are unfamiliar with analog to digital conversion, I suggest that you pause this video and watch my introductory video first, where I explain the concept and show how this particular chip is used. What you see here is a typical joystick found in electronic kits for Raspberry Pi. My joystick has 5 pins, 2 for power, 2 for direction, X and Y, and a button. Internally, the joystick consists of 2 potentiometers, where X and Y outputs are signals from the middle pins. The X and Y output voltage will vary between 0 and 3.3 volts. My joystick has actually 5 volts printed on, but you must use 3.3 volts in Raspberry Pi circuits, otherwise you will damage the Pi. The button is activated by pressing the joystick shaft down. Mine closes the circuit with the ground pin, which means it can be used in a pull-up resistor configuration. The angled headers will work in a breadboard, but I prefer to replace them with straight ones. This is relatively simple if you have some basic soldering skills. Let's have a closer look at the circuit. My circuit consists of the joystick connected to the Pi through the ADS7830 chip and 4 LEDs with resistors. The LEDs will be used to demonstrate visually the position and function of the joystick. Let's get on with the code. I typically start simple projects like this one with a skeleton program such as this. Such framework provides for a basic layout that handles common program exit scenarios. The SMBus library is a simple interface that allows interacting with the ADC chip using the I2C protocol. I will be using the primary I2C bus in this project, indicated by number 1 here. Communication with the ADS7830 chip is conducted by writing numerical commands to the bus, with each of them referring to one of the 8 analog inputs. This program will only use 2 of them, belonging to analog input 6 and 7. LEDs are declared using their respective pins. The PWM variety allows them to be dimmed, which will work well in this joystick demo. Output components such as LEDs need to be explicitly closed when the program exits to restore the GPIO ports to default. Let's add some code to test the ADC chip by displaying the readings in the terminal. The read ADS7830 function will provide me with the reading of a given input as a value between 0 and 255. This read function can be used in a loop to display the joystick position, for example, 10 times a second. The joystick is in its neutral position when the program starts, with the X and Y values somewhere in the middle of the 255 value range. Theoretically, this should be 127, but in practice, a joystick will be always slightly off. This phenomenon is called drift, and it affects all analog joysticks. I will show you in a moment how to compensate for it. Moving the shaft to the left or bottom will change the values towards 0, while the opposite direction will change the values red towards 255. Let's have a closer look at the drift issue now. There are several reasons why the values shown in the neutral position are not 127 and are not 100% stable. The spring mechanism that centers the joystick is not 100% reliable. Additionally, the joystick may be affected by vibrations caused by me bumping the table, the ADC error margin, and the power supply stability too. This cannot be ignored, otherwise whatever you control with the joystick would behave erratically. Compensating for drift is not simple. The neutral values will be likely different every time the joystick returns to its normal position. Also, the behavior will change as the joystick ages, and each joystick is different. Looking at mine, the neutral values seem to fluctuate between 109 and 127 right now. One way to deal with the drift is to default readings to 127 within the known fluctuation range. I will make a separate function to provide the drift tree readings, making it roughly symmetric around the 127 value. I will define the neutral as being between 110 and 140 for my joystick, but you will need to adjust it in your case. It is also a matter of balance, as too wide of a margin will make the joystick less responsive. Depending on the joystick application, drift compensation may require a more refined method, but this one is sufficient in many cases, including projects where a joystick is used to control a motor speed. Let's modify this project to connect the LEDs to the joystick so you can see exactly how the joystick signal looks like. The display loop and the sleep statement can be deleted now, as I will use GPIO 0 as source value method. I will accomplish this with two generator functions, one for minimum or below neutral if you prefer, and one for maximum or above neutral. Starting with the read minimum function, the joystick position is read first. PWM LED brightness is set by assigning a value between 0 and 1 to them. That requires a bit of math to convert to that range from the ADC readings of 0 to 255. If the joystick is below neutral, taking the drift into account, it is calculated as a fractional value between 0 and 1. This function will return 0 if the joystick is in the above neutral range. The read maximum function performs a similar task, providing values between 0 and 1 if the joystick is in the above neutral position. Readings below the neutral default to 0. The read minimum and read maximum generator functions are directly compatible with the source property of the PWM LED. The LEDs will automatically obtain the brightness value from these functions 100 times a second. This is a very efficient process which employs multi-threading, but it needs to be correctly deactivated before the program exits. Here's the final project in action. The LEDs will follow the joystick position. This is a case where a better handling of the neutral position may be needed to make the dimming process smoother, and I have a separate video on that topic. That is all for this tutorial. I hope you liked it. Thanks for watching.